Welcome back to Titans of the Air, the channel that dives deep into the history books, past the headlines and the famous aces, to find the hidden figures, the forgotten geniuses whose vision shaped the very technology of air power. We often think of history as a neat progression, a series of logical steps from propeller to jet, from subsonic to supersonic. We celebrate the famous names, Whittle in Britain, von Ohain in Germany, as the fathers of the jet age. But the story of innovation is rarely so simple, rarely so clean. Often, the true pioneers, the ones who saw the future years, even decades, before anyone else, are lost in the noise. Their contributions overshadowed, their names relegated to footnotes, if mentioned at all. Tonight, we pull back the veil on one such figure, an engineer working in relative obscurity, wrestling with the fundamental principles of propulsion at a time when the entire aviation world was utterly convinced that the propeller was, and always would be, king. He wasn't just refining, he was dreaming. He saw a different kind of power, a reaction engine, a gas turbine spewing fire and force, capable of speeds and altitudes unimaginable with pistons and props. He drew the blueprints, he ran the calculations, he even built the first, sputtering, dangerous prototypes, years before the names Whittle and von Ohain became synonymous with the jet engine. He conceived the jet war era before the Second World War even cast its long shadow. Yet history has largely forgotten him. This is the story of the forgotten engineer who built the jet war era before the war even began. Before we delve into this incredible lost chapter of aviation history, if you believe that the true pioneers, regardless of fame, deserve to have their stories told, then I need you to engage with our mission. First, hit that subscribe button and make sure you ring the notification bell. It ensures you won't miss any of these crucial historical deep dives. Second, give this video a like. Your support helps propel these stories to a wider audience. And finally, drop a comment down below. Let us know what country and city you're watching from. It's always inspiring to see our global community of aviation history enthusiasts gather here. Now, let's travel back to a time when the sky belonged to the piston engine, and the roar of a jet was a sound that existed only in the mind of one forgotten man. The year is 1928. Calvin Coolidge is in the White House. The roar of the jazz age fills the airwaves, and the undisputed king of the sky is the propeller. Aviation is still a relatively young marvel, defined by the staccato thunder of radial engines, the intricate dance of pistons and crankshafts, the blur of spinning wooden or metal blades biting into the air. Charles Lindbergh has conquered the Atlantic just a year prior, a triumph of endurance powered by a single Wright whirlwind piston engine. Biplanes still dominate military air forces. Though sleek, all-metal monoplanes are starting to hint at a faster future. Speed is measured in increments, maybe 200, perhaps 250 miles per hour for the absolute cutting-edge racing planes. Altitude is a struggle against thinning air, engines gasping for oxygen above 20 feet. The limitations seem fundamental, baked into the very physics of the internal combustion engine and the propeller it drives. As propeller tips approach the speed of sound, their efficiency plummets, creating shock waves, vibration, hitting an invisible wall. Bigger engines mean more weight, more drag, diminishing returns. The future. According to virtually every leading aeronautical mind of the era, the brilliant engineers at Wright Aeronautical, Pratt & Whitney, Rolls-Royce, Bristol, lies in refining the piston engine. Higher compression ratios, better superchargers, more efficient propeller designs. The goal is evolution, not revolution. Nobody, absolutely nobody in a position of power or influence is seriously considering a completely different form of propulsion for aircraft, except perhaps in the realm of speculative fiction or the occasional easily dismissed crackpot patent application. Enter Secondo Campini, an Italian engineer born in Bologna in 1904, barely 24 years old in 1928, possessed of a restless intellect, a fascination with fluid dynamics, and a profound dissatisfaction with the limitations of the propeller. Campini wasn't an established figure. He wasn't part of the major aircraft manufacturers or engine companies. He was a young, independent thinker, captivated by the emerging science of rocketry and the fundamental principle of Newton's third law. For every action, There is an equal and opposite reaction. While others saw the future in perfecting the complex mechanics of the piston engine, Campini looked at the simplest form of propulsion, pushing mass backwards to move forward. Rockets did it with explosive chemical reactions. But could it be done with air? Could you design an engine that sucked in air, compressed it, heated it, and then expelled it at high velocity, generating thrust without the need for a complex speed-limited propeller? The basic concept of the gas turbine wasn't entirely new. Patents for stationary turbines existed, primarily for power generation or ship propulsion. But these were massive, heavy, inefficient machines. The idea of shrinking a gas turbine down, making it light enough, powerful enough, and efficient enough to power an aircraft seemed utterly ludicrous to the established engineering community. The materials required to withstand the incredible temperatures and stresses inside a compact, high-speed turbine simply didn't exist, or so conventional wisdom dictated. The aerodynamic understanding of airflow within the complex passages of a compressor and turbine operating at high speeds was rudimentary at best. The combustion process, achieving stable, continuous burning within a high-velocity airstream, was a black art. It was a problem riddled with seemingly insurmountable obstacles, but Campini possessed a unique, perhaps naive, perspective. He wasn't burdened by decades of experience telling him what couldn't be done. He approached the problem not as a traditional engine designer, but as a fluid dynamicist. He saw the challenge primarily as one of efficiently accelerating a mass of air, and he had a radical, almost bizarrely simple shortcut in mind, one that bypassed the most significant hurdle facing true gas turbine development: the turbine itself. Building turbine blades that could survive the incandescent heat and incredible rotational forces was the holy grail, the metallurgical nightmare that would consume engineers for another decade. Campini's idea? Don't have a turbine drive the compressor. Instead, use a conventional, readily available piston engine to drive the compressor. His concept, which he began sketching and patenting as early as 1931, was for what would later be called a motor jet or thermojet. Air would be drawn in through an intake at the front. It would then be compressed by a multi-stage axial or centrifugal compressor, just like in a true turbojet. But instead of that compressor being driven by a turbine spun by the hot exhaust gases, it would be driven by a separate internal piston engine connected via a gearbox. After compression, fuel would be injected into the compressed air and ignited in a combustion chamber. The resulting hot, high-pressure gas would then be expelled through a nozzle at the rear, generating thrust. It was, on the surface, a hybrid, a kludge, a seemingly backward step, using the old technology, piston engine, to power the new, jet propulsion. To proponents of pure jet propulsion, a tiny, unheard minority at the time, it seemed unnecessarily complex and heavy, retaining the limitations of the piston engine's altitude performance. To the established piston engine manufacturers, it seemed utterly pointless. Why go to all the trouble of building a complex compressor and combustion system just to generate thrust that could be achieved more simply, or so they thought, with a propeller? Campini's design was met with almost universal skepticism, often bordering on ridicule, from the Italian aviation establishment and the wider international community. It was seen as an inefficient Rube Goldberg contraption, a theoretical curiosity with no practical application. He lacked funding. He lacked facilities. He lacked credibility. He was a lone voice, proposing a radical departure from accepted principles, armed with little more than blueprints and calculations that seemed to defy conventional engineering wisdom. Yet, Campini possessed an almost fanatical self-belief and a relentless drive. He saw his motorjet not as a compromise, but as a pragmatic first step. It allowed him to tackle the complex aerodynamic challenges of the compressor, the intake, the combustion chamber, and the nozzle without having to simultaneously solve the near-impossible metallurgical problem of the high-temperature turbine. It was a way to get a reaction-propelled aircraft flying, using existing reliable components for the core power source. He believed, perhaps rightly, that once the principle of jet propulsion was demonstrated, Once the limitations of the propeller were starkly revealed in flight, then the resources and focus would shift towards developing the materials and designs needed for a true turbojet. For nearly a decade, Campini toiled in relative obscurity, struggling to gain support. He published papers, filed patents across Europe and in the United States. His 1934 U.S. patent clearly outlines the motorjet concept, built small-scale models, and relentlessly lobbied the Italian Air Ministry, Regia Aeronautica, and aircraft manufacturers. He faced constant rejection. His calculations were questioned. His designs were deemed impractical. The prevailing view remained firmly fixed on bigger, better piston engines and faster spinning propellers. The Caproni Aircraft Company, known for its large bombers, showed some initial interest, intrigued by the potential for high-altitude flight without the complexities of multi-stage superchargers, but official funding remained elusive. The Regia Aeronautica, while investing heavily in modernizing its fleet with advanced monoplanes like the Machi C200 and Fiat G50, saw them purely as platforms for proven Fiat and Alfa Romeo piston engines. Campini's radical propulsion system was simply too far outside their conceptual framework. Too risky, too unproven. He was trapped in a classic innovator's dilemma. He couldn't get funding without proof, and he couldn't get proof without funding. It seemed his dream, conceived years before Whittle or von Ohain had even seriously begun their work, was destined to remain just that. A dream, confined to paper, a footnote in the history of what-ifs. But Campini was nothing if not persistent. And the looming shadow of war, the accelerating pace of military aviation development across Europe in the late 1930s, was about to give his stupid idea one last, desperate chance. He just needed someone, anyone, with the resources and the audacity to take a gamble on the future he envisioned. Campini's relentless lobbying and the undeniable theoretical appeal of reaction propulsion, however unconventional his specific approach, finally found a receptive, albeit cautious ear. Benito Mussolini's fascist regime in Italy, obsessed with projecting an image of technological prowess and national prestige, saw a potential propaganda victory in being the first nation to conquer the air with jet power. While the Air Ministry remained deeply skeptical about the military applications of Campini's motorjet, the allure of a high-profile first was too tempting to ignore completely. In early 1934, after years of persistent effort by Campini, the ministry cautiously approved a small contract, not for a full aircraft, but for the development and testing of his thermojet engine concept, channeled through the Caproni Company. This wasn't a blank check. It was a shoestring budget, enough to keep the idea alive, but far from the resources being poured into conventional engine development. Campini, finally given a chance, however limited, threw himself into the work with ferocious intensity. He partnered with Caproni's engineers at their Taliedo facility near Milan, a team more accustomed to designing large, multi-engine bombers than wrestling with the high-speed aerodynamics of internal duct flow. The challenges were immense, stretching the limits of 1930s technology and understanding. The heart of the system was the compressor. Campini opted for a three-stage variable-pitch ducted fan design, essentially 3 sets of propeller-like blades enclosed within a carefully shaped duct. Variable pitch was crucial, allowing the blade angles to be adjusted to maintain efficiency across different speeds and altitudes, a concept far ahead of its time for internal compressors. Designing these blades, determining the optimal airfoil shapes, the twist, the pitch change mechanism, all within the confines of a narrow duct, operating at high speeds and subject to complex aerodynamic interactions. It was a monumental undertaking. Computational fluid dynamics didn't exist. Wind tunnel testing for internal flows was rudimentary. Much of the design relied on Campini's intuition, laborious hand calculations, and painstaking trial and error with small-scale models. The piston engine chosen to drive this compressor was a 900-horsepower Isotta Fraschini L 121R C40, a liquid-cooled V12, relatively powerful and reliable for its day, but still a massive, heavy piece of machinery to bury inside an aircraft fuselage. Integrating it, designing the gearbox to transfer power efficiently to the compressor shaft, and ensuring adequate cooling for this buried engine, all while minimizing drag and weight, presented huge packaging and thermal management problems. Then came the combustion system, arguably the most radical part of Campini's vision after the motorjet concept itself. Instead of discrete combustion cans like early Whittle or von Ohain designs, Campini envisioned injecting fuel directly into the compressed air behind the compressor, turning the entire rear section of the engine duct into a massive afterburner. Rings of fuel injectors would spray atomized kerosene into the high-velocity airflow, which would then ignite and burn continuously, dramatically increasing the temperature and velocity of the exhaust gas exiting the rear nozzle. This duct-burning concept promised significantly higher thrust than just the compressor alone could provide, effectively acting as a primitive afterburner integrated into the core engine cycle. However, achieving stable combustion in such a high-speed turbulent airflow, without melting the duct walls or causing violent pressure fluctuations, was a black art. Flame holder design, fuel atomization, ignition systems. These were all areas where Campini and the Caproni team were venturing into almost completely unknown territory. The nozzle design was also critical. To achieve maximum thrust, the hot, high-pressure exhaust gas needed to be accelerated smoothly to the highest possible exit velocity. Campini designed a variable geometry nozzle, a complex clamshell-like mechanism at the rear that could change the exit area, theoretically optimizing thrust across different flight conditions. Another concept far ahead of the mainstream jet engine thinking of the time. Development was slow, arduous, plagued by setbacks. Compressor blades failed under stress. Combustion proved unstable, prone to violent chugging or simply blowing out. The gearbox transferring power from the piston engine to the compressor was a constant source of vibration and mechanical failures. Cooling the buried Isotta Fraschini engine was a nightmare, requiring complex ducting and radiators that added weight and drag. The variable pitch mechanism for the compressor blades proved difficult to implement reliably. The variable nozzle frequently jammed. Each problem required laborious analysis, redesign, remanufacturing of custom parts, and more testing, all conducted under the constant pressure of a skeptical air ministry and a shoestring budget. Campini, though brilliant, was also reportedly difficult to work with. Passionate, stubborn, utterly convinced of his own vision, sometimes clashing with the more conservative Caproni engineers. Yet, despite the immense challenges, they persisted. By 1939, after nearly 5 years of painstaking work, they had a functional, ground-testable prototype engine. It was a massive, complex, heavy beast, a tangled maze of plumbing, ducting, gears, and wires. It barely resembled the sleek, elegant turbojets that Whittle and von Ohain were secretly developing in Britain and Germany. But when it fired up on the test stand, strapped down with heavy chains, it produced a sound unlike anything heard before at Taliedo. Not the staccato bark of a piston engine, but a deep, powerful, continuous roar, accompanied by a blast of searing hot air from the rear nozzle. It produced thrust. Not much initially. The early prototypes were notoriously inefficient, barely producing more thrust than the piston engine consumed in driving the compressor. But it was reaction thrust. It was proof, however flawed, that Campini's concept could work. The looming threat of war in Europe added a new urgency. While the motorjet was still far from a practical combat engine, the potential propaganda value of flying the world's first jet aircraft spurred the Italian government to finally authorize the construction of a flying test bed. Caproni was tasked with building an airframe specifically designed to house Campini's monstrous engine. The result was the Caproni-Campini N1, sometimes designated CC-2, an aircraft as unconventional as its power plant. It was a bulky, somewhat ungainly-looking machine, resembling a barrel-chested propeller plane that had swallowed its own prop. It had a large circular air intake in the nose, leading straight to the 3-stage compressor driven by the Isotta Fraschini V12 buried deep within the fuselage. The pilot sat in a cockpit perched awkwardly above the main engine duct. The rear fuselage tapered to the variable geometry nozzle. The wings were conventional, low-mounted, straight-tapered. The landing gear was retractable. It was designed not for speed or combat, but purely as a flying laboratory, a proof-of-concept demonstrator. Construction proceeded through 1939 and into 1940, even as Italy prepared to enter World War II alongside Germany. The challenges of integrating the complex engine into the airframe were immense. Cooling remained a critical issue. The sheer weight of the combined piston engine, compressor, gearbox, and associated plumbing resulted in an aircraft that was significantly heavier than comparable propeller-driven fighters of the era. Finally, on August 27, 1940, at the Caproni facility in Taliedo, history was made, albeit almost unnoticed by a world consumed by the Battle of Britain raging across the English Channel. With legendary test pilot Mario De Bernardi at the controls, the Caproni Campini N1 sluggishly rolled down the runway, lifted into the air, and completed a short, tentative but successful 10-minute flight. It was, arguably, the first public flight of a jet-propelled aircraft. Von Ohain's Heinkel He 178 had flown secretly almost exactly a year earlier, in August 1939, but remained classified. Campini was ecstatic. His decade of struggle, of ridicule, of relentless belief had culminated in this moment. His thermojet flew. The flight itself was far from spectacular. The N1 was severely underpowered. The thrust generated by the motorjet system, especially without the duct burning engaged, it was deemed too unreliable for the first flights, was barely enough to overcome the aircraft's considerable weight and drag. Its top speed was estimated at a pathetic 233 miles per hour, significantly slower than the propeller-driven fighters it was supposed to herald the replacement of. Its climb rate was abysmal. It was noisy, inefficient, and complex. By almost every practical metric, it was a failure. The skeptics felt vindicated. The Air Ministry, already grappling with the demands of a real war and the shortcomings of its conventional air force, saw little military value in this slow experimental curiosity. Yet, the propaganda value was undeniable. On November 30, 1941, De Bernardi flew the N1 from Taliedo to Guidonia, near Rome, a flight of about 15 minutes, which was widely publicized by the fascist regime as a world record for jet flight, conveniently ignoring the He 178's earlier secret flights and the Gloster E-2839 powered by Whittle's engine, which had flown in May 1941 but was also still classified. The Fédération Aéronautique Internationale, FAI, even recognized the flight. For a brief, shining moment, Secondo Campini was hailed as a national hero, the father of Italian jet propulsion, the man who had ushered in a new era. But the reality behind the headlines was grim. The N1 was a technological dead end. It was too slow, too heavy, too complex. The duct burning system, when engaged, provided a modest boost in thrust, but consumed fuel at an alarming rate and was dangerously unreliable, prone to overheating and flameouts. Further development was hampered by the worsening war situation, Italy's limited industrial resources, and the persistent skepticism of the military establishment. While Germany and Britain, spurred by the urgent demands of aerial combat, were rapidly advancing their true turbojet designs, the Me-262, the Gloster Meteor, Campini's motorjet remained a fascinating but ultimately impractical hybrid. The N1 made only a handful more flights before being grounded, eventually damaged during an Allied bombing raid and largely forgotten. Campini, his brief moment of fame overshadowed by the rapid advancements elsewhere and the eventual collapse of fascist Italy, faded from the forefront of jet propulsion history. His pioneering vision, his conception of a reaction engine aircraft years before the established figures, his pragmatic, if ultimately flawed, motorjet solution, all became a historical footnote. He was the man who flew first, publicly, but whose technology was a blind alley. He had built the jet war era conceptually on paper and even in primitive hardware before the war even began, only to be left behind when the real jet age, powered by the true turbojet engines he couldn't quite reach, finally dawned. The flickering candle of fame ignited by the Taliedo to Guidonia flight cast Secondo Campini as a momentary national icon, a symbol of Italian ingenuity boldly stepping into the future. The fascist propaganda machine seized upon the N1, plastering its bulky, unconventional image across newsreels and magazines, proclaiming Italy the leader in the dawning age of jet propulsion. For Campini, it must have been a moment of intense, almost unbearable vindication. After nearly a decade of relentless struggle, facing down skepticism, ridicule, and crushing funding limitations, his machine, his idea, had taken flight and captured the world's attention, however fleetingly. He had forced the establishment to acknowledge the reality of reaction propulsion, dragging the concept from the realm of theoretical fantasy into tangible, noisy, kerosene-burning reality. He had achieved his first, a public demonstration that fundamentally challenged the universal reign of the propeller. Yet, beneath the veneer of propaganda and the genuine technical achievement of getting the complex motorjet airborne, the harsh realities of the N1's performance, or lack thereof, could not be ignored by those who understood the brutal calculus of aerial warfare. The engineers within Caproni, the pilots within the Regia Aeronautica's test centers, and indeed Campini himself, knew the truth. The N1 was not a weapon. It wasn't even a particularly promising prototype. It was a fascinating, deeply flawed, and potentially dangerous curiosity. Its Achilles heel remained its crippling lack of power relative to its enormous weight and complexity. The 900 horsepower Isotta Fraschini piston engine, while respectable for its time, was simply inadequate for the task of driving a compressor large enough to generate significant reaction thrust, especially when burdened by the weight of the compressor itself, the heavy gearbox, the extensive cooling systems, and the robust structure needed to house it all. The net thrust produced, particularly without the problematic duct burning engaged, was pathetic. The N1 struggled to take off, climbed like a waterlogged duck, and, as mentioned, could barely exceed 230 miles per hour in level flight, a speed easily surpassed by contemporary propeller-driven fighters like the Spitfire, the Bf-109, and even Italy's own Machi C-202 Folgore, which were pushing towards, and sometimes exceeding, 400 mph. The very technology the N1 was supposed to render obsolete was, in fact, dramatically outperforming it in every meaningful metric. Speed, acceleration, climb rate, maneuverability, range, and operational ceiling. The contrast was stark, embarrassing, and ultimately damning. The motorjet concept, while bypassing the immediate challenge of high-temperature turbine metallurgy, had simply traded one set of insurmountable problems for another. The weight and complexity penalty of integrating a large piston engine inside the jet's thermodynamic cycle crippled its potential. Furthermore, the duct burning system, Campini's innovative but temperamental afterburner, proved to be a double-edged sword. When it worked, it provided a noticeable, though still inadequate, thrust boost. But when it worked was the operative phrase. Achieving stable combustion within the long, relatively low-pressure duct behind the compressor was incredibly difficult. The system was prone to violent pressure oscillations, known as chugging or rumble, inefficient burning that produced more smoke than thrust, and catastrophic flameouts. Pushing the duct burning to its theoretical maximum often resulted in overheating the rear fuselage structure, threatening the integrity of the airframe itself. It consumed fuel at a prodigious rate, drastically limiting the aircraft's already poor endurance. It was, in essence, a dangerous party trick, impressive on the test stand, perhaps, but far too unreliable and inefficient for operational use. The Italian Air Ministry, initially buoyed by the propaganda victory, quickly sobered as the NN1's flight test reports trickled in. They were embroiled in a real war, facing technologically advanced and numerically superior Allied air forces in North Africa and the Mediterranean. Their urgent need was for effective combat aircraft now. They needed more Machi C-202s and C-205s, more Reggiani Re 2001s and Re 2005s, excellent piston-engine fighters that could at least hold their own against Allied counterparts. Diverting precious resources, skilled engineers, scarce materials like high-strength steel alloys, limited factory capacity, towards a slow, unreliable, unarmed experimental aircraft like the N1, an aircraft with no clear path to military utility, became increasingly unjustifiable. The skepticism that had always simmered beneath the surface quickly resurfaced, solidifying into official disinterest. Campini, despite his brief moment in the sun, found himself once again on the outside, His project starved of the resources needed for meaningful further development. He had demonstrated a principle, but failed to deliver a practical machine. While Campini grappled with the inherent limitations of his motor jet and the indifference of his own government, the seeds of the true jet age were rapidly germinating elsewhere, in conditions of far greater secrecy and ultimately far greater consequence. In Great Britain, Frank Whittle, a driven RAF officer who had conceived of the turbojet independently and patented his design even earlier than Campini in 1930, was after years of similar struggles against official skepticism and underfunding, finally seeing his vision take flight. His W-1 engine, powering the Gloster E-2839 experimental aircraft, had made its first flight in May 1941, just 6 months before the N-1's widely publicized Rome flight. Though kept secret from the public, the performance of Whittle's aircraft, even in its early underpowered state, was vastly more promising than the N-1. It was smaller, lighter, and crucially, its engine represented a fundamentally more efficient and scalable path towards high-speed flight. Even more significantly, in Nazi Germany, Hans von Ohain, working with the Heinkel Company and spurred by the Reich Air Ministry's urgent quest for technological superiority, had already achieved the world's first, albeit secret, pure turbojet flight with the Heinkel He-178 in August 1939. By the time Campini's N-1 was making headlines in late 1941, German engineers at BMW, Junkers, and Heinkel Herth were deep into the development of axial flow turbojets, engines like the BMW 003 and Junkers Umo 04, that were vastly more powerful and sophisticated than anything Whittle or Campini had yet produced. These German engines, benefiting from massive state investment and ruthless prioritization driven by wartime necessity, were rapidly overcoming the immense metallurgical and aerodynamic challenges that Campini's motor jet had cleverly bypassed but ultimately failed to circumvent. They were developing cobalt and nickel-based superalloys capable of withstanding the hellish temperatures inside the turbine. They were mastering the complex aerodynamics of multi-stage axial compressors. They were designing efficient annular combustion chambers. They were, in short, building the engines that would power the Messerschmitt Me-262, the world's first operational jet fighter, an aircraft that would appear in the skies over Europe less than 3 years later, rendering all contemporary aircraft, including Campini's N-1, instantly obsolete. Campini himself was likely unaware of the specific details or the rapid pace of these secret British and German programs during the war years, but the stark performance limitations of his own N-1 must have become painfully apparent as flight testing continued, however sporadically. He had hit a wall, a ceiling imposed by the fundamental physics of his hybrid design. The weight and inefficiency of the internal piston engine were an anchor he simply couldn't shed. While his concept had allowed him to be the first to publicly demonstrate jet flight, it had also locked him into a technological cul-de-sac. He had solved the wrong problem, or rather solved a part of the problem by creating an even bigger one elsewhere. His innovation was real, his vision prescient, but his chosen implementation was flawed, a stepping stone that led nowhere. The limited flight testing program of the Caproni Campini N-1 reflected this reality. After the initial fanfare of the 1940 and 1941 flights, the aircraft flew only intermittently. Resources were diverted to more pressing wartime production. The technical challenges, particularly with the duct burning system and the overall low thrust-to-weight ratio, proved intractable without major redesign and investment that was simply not forthcoming. Test pilots reported difficult handling characteristics, sluggish acceleration, and a constant unnerving vibration from the complex powertrain. The aircraft was, by all accounts, a disappointment, a technological marvel that failed to deliver on its implicit promise of speed and performance. Its fate was sealed by the declining fortunes of war for Italy and the eventual Allied invasion. The two prototypes, sources differ on whether a second was fully completed or just partially assembled, were grounded sometime in 1942 or 1943. One was reportedly damaged beyond repair during an Allied bombing raid on the Guidonia airfield near Rome. The other survived, partially dismantled, eventually being shipped to the UK after the war for study, a forgotten curiosity, before ultimately returning to Italy for museum display. Secondo Campini's moment had passed. The jet age he had envisioned, The era of reaction propulsion he had arguably been the first to publicly demonstrate in the air was dawning, but it was being forged by others, by Whittle's dogged persistence and von Ohain's state-backed resources, by the brutal imperatives of total war, and by the fundamental superiority of the true turbojet cycle. Campini, the forgotten pioneer, had opened a door, but it was a door that led only to a dead end, while the real highway to the future was being paved elsewhere, in secret, leaving his name and his strange hybrid machine behind as little more than a historical footnote. The end of World War II in 1945 brought not vindication for Secondo Campini, but a harsh, undeniable verdict delivered by the victorious roar of Allied and captured German jet engines. The Gloster Meteor was operational, facing off against the Me-262 in the final chaotic months of the European conflict. American engineers, jump-started by the acquisition of Whittle's technology, and captured German engines and data through operations like Project Paperclip, were rapidly developing their own turbojets. The P-80 Shooting Star, powered by a derivative of the de Havilland Goblin, was already flying. The world Campini had envisioned, the world of reaction propulsion, had arrived with a vengeance, but it had arrived via a different path, a path forged in the crucible of total war, leveraging breakthroughs in metallurgy and aerodynamics that had simply not been available, or perhaps even conceivable, during his primary development period in the 1930s. His motorjet, the N1, sitting damaged and ignored in Italy, was no longer just an underperformer, it was a relic, an evolutionary dead end, a fascinating but ultimately irrelevant curiosity in the face of the demonstrated power and relative simplicity compared to the motorjet hybrid of the true turbojet cycle. Whittle and von Ohain, once obscure figures like himself, were now being lauded as the founding fathers of this new age, their names etched into the annals of aviation history. Campini, the man who arguably achieved the first public jet flight, the man whose patents predated some of the key developments elsewhere, found himself increasingly sidelined, his contributions minimized or outright dismissed. Why was Campini relegated to the footnotes while Whittle and von Ohain ascended to legendary status? Several factors conspired against his legacy. Firstly, and most critically, his chosen technology, the motorjet, was fundamentally flawed in its reliance on the heavy, altitude-limited piston engine. While it was a clever engineering compromise to overcome the immediate hurdle of turbine technology, it baked in limitations that prevented it from ever achieving the high thrust-to-weight ratios and high-altitude performance that characterize the true turbojet. It was a bridge, but a bridge to nowhere. Whittle and von Ohain, by tackling the much harder problem of the gas turbine directly, had unlocked the true potential of jet propulsion. Their path was far more difficult initially, demanding breakthroughs in materials science that stretched the very limits of possibility, but the eventual reward was immensely greater. Secondly, the context of wartime secrecy played a huge role. Both the British and German turbojet programs were conducted under intense classification. The He-178's 1939 flight and the Gloster E-2839's 1941 flight, while preceding the N1's public debut, in the Gloster's case, or happening significantly earlier, in the Heinkel's, were unknown to the wider world, including Italy, until after the war. Campini's public flight in late 1941 appeared to be the first, securing him temporary recognition, but the subsequent revelation of the earlier, more advanced, and militarily significant secret programs inevitably overshadowed his achievement. He flew first publicly, but others had flown higher, faster, and more meaningfully in secret. Thirdly, the impact of wartime necessity and resources cannot be overstated. While Campini struggled with meager funding and official skepticism in Italy, a nation with limited industrial capacity and competing military priorities, the British and German programs eventually received massive state backing. The relentless demands of World War II created an environment where radical, potentially war-winning technologies like the turbojet were pursued with a desperation and a level of investment that Italy simply could not match. The development of heat-resistant alloys, the refinement of axial compressor aerodynamics, the solutions to combustion instability. These breakthroughs were achieved at an accelerated pace driven by the existential struggle for air superiority. Campini was essentially a lone inventor with limited industrial support, trying to compete with national-level wartime R&D efforts. It was an unequal fight he was destined to lose. Fourthly, the post-war narrative was largely written by the victors, British and American historians, celebrating their own pioneers like Whittle and the engineers who rapidly developed jets like the P-80 and F-86, naturally emphasized their own lineage. German engineers, brought over through paperclip, contributed their knowledge and often claimed precedence, as with von Ohain, further shaping the story. Italy, as a defeated Axis power, had less influence on the historical record, and Campini's already marginalized contribution became even easier to overlook. The EU-1 was seen as a quirky artifact of a defunct regime, not a pivotal step in the main line of jet development. Did any of Campini's specific technical innovations find echoes in later designs, even if his core motorjet concept failed? Some historians argue yes, albeit indirectly. His work on variable pitch compressor blades, while difficult to implement reliably with 1930s technology, foreshadowed later developments in variable stator vanes used to improve compressor efficiency and stability across a wider range of operating speeds in more advanced turbojets. His concept of duct burning, essentially integrating an afterburner into the main engine flow path, while crude in the N1, clearly anticipated the afterburners that would become standard equipment on virtually all supersonic military aircraft, providing crucial bursts of extra thrust for takeoff, climb, and combat maneuvers. His early exploration of variable geometry exhaust nozzles, designed to optimize thrust under different conditions, also predicted the complex converging-diverging nozzles essential for efficient supersonic flight in later generations of jet engines. However, attributing a direct linear influence is difficult. These concepts, variable stators, afterburners, variable nozzles, were also being explored, often independently by engineers in other countries facing similar aerodynamic and thermodynamic challenges. Campini's patents and publications certainly put these ideas into the public, or at least the engineering domain, potentially influencing or stimulating thought elsewhere. But proving a direct causal link, especially given the secrecy and parallel development efforts of the era, is challenging. It's perhaps fairer to say Campini was grappling with the right problems and exploring concepts that would become crucial, even if his specific implementation of the core engine cycle was ultimately unsuccessful. He saw the need for variable geometry in compressors and nozzles, and the potential of augmenting thrust through fuel injection in the exhaust stream long before these became mainstream. In the post-war years, Campini did not simply disappear. He continued to work, to invent, to advocate for his ideas, though largely outside the major engine manufacturing conglomerates that now dominated the rapidly evolving jet age. He consulted on various projects, explored ramjet and pulsejet concepts, and even proposed innovative hybrid designs. He moved to the United States for a period, working with Curtiss-Wright and other companies, contributing his expertise in fluid dynamics and propulsion, though never again achieving the prominence, however fleeting, of the N1 era. He remained a passionate, if somewhat peripheral figure in the world of aerospace engineering until his death in 1980. His legacy remains complex and debated among aviation historians. Was he a true father of the jet age, unfairly overlooked? Or was he a brilliant but ultimately misguided engineer who pursued a technological dead end? The truth perhaps lies somewhere in between. He undeniably possessed extraordinary vision, grasping the potential of reaction propulsion years before many of his contemporaries. He demonstrated remarkable persistence, overcoming immense obstacles to turn his radical concept into flying hardware. He achieved a significant historical first with the public flight of the N1. However, his chosen technological path, the motorjet, proved fundamentally flawed, unable to compete with the true turbojet. His work, while conceptually innovative in certain aspects, duct burning, variable geometry, did not directly lead to the mainstream breakthroughs that defined the jet engines powering the next generation of aircraft. He remains, therefore, a fascinating figure, a pioneer who pointed towards the future, built a machine that touched it briefly, but ultimately couldn't provide the engine to truly conquer it. He was the engineer who conceived the jet war era before the war began, but whose name, unlike Whittle or von Ohain, is rarely spoken when the thunder of modern jets fills the sky. So, where does Secondo Campini fit in the grand, often mythologized, narrative of the jet age? He remains an enigma, a figure perpetually dwelling in the footnotes rather than the main text. Unlike Whittle, whose dogged determination eventually yielded the engines that powered the first Allied jets and laid the groundwork for Rolls-Royce's dominance, or von Ohain, whose state-backed efforts produced the world's first turbojet flight and contributed significantly to Germany's wartime jet programs, Campini's legacy lacks that clear, linear connection to subsequent, successful engine development. His N1, while a testament to his ingenuity and persistence, ultimately demonstrated the limitations of the motorjet concept rather than its potential. It flew, yes, but it flew too slowly, too inefficiently, too unreliably to influence the trajectory of military aviation in any meaningful way. It was a technological curiosity, a bold experiment that answered a question perhaps no one else was asking. While the critical questions about high-temperature metallurgy and high-speed compressor aerodynamics were being answered decisively elsewhere. Yet to dismiss Campini as merely a misguided inventor pursuing a dead end feels profoundly unjust. One must consider the context of his work. In the late 1920s and early 1930s, when he first conceived and patented his motorjet, the very idea of reaction propulsion for aircraft was radical, bordering on science fiction. The materials science that would enable practical turbojets simply did not exist. The understanding of high-speed aerodynamics, particularly internal compressible flow, was rudimentary. In this environment, Campini's motorjet wasn't just a kludge. It was a pragmatic, almost logical engineering compromise. It was an attempt to achieve reaction thrust by leveraging existing, reliable piston engine technology for the power source, isolating the more manageable, though still incredibly difficult, challenges of compressor and duct design. It was, perhaps, the only way someone without the vast resources of a major government or corporation could even attempt to build a jet engine in that era. His patents, particularly the detailed 1934 U.S. patent, clearly articulate the core principles of a ducted fan system with afterburning, demonstrating a sophisticated understanding of thermodynamics and fluid dynamics far ahead of many contemporaries. He wasn't just tinkering, he was engineering, based on sound theoretical principles, albeit constrained by the technology of his time. Furthermore, the sheer audacity of his vision deserves recognition. At a time when the entire aviation world was focused on squeezing incremental gains from piston engines, Campini was envisioning a fundamentally different way to fly. He saw, years before most, that the propeller was a barrier, that true high-speed, high-altitude flight required harnessing the power of reaction. His N1, however flawed its performance, was a physical manifestation of that vision, a tangible challenge to the status quo. The publicity surrounding its flights, even if exaggerated by propaganda, undeniably helped to introduce the concept of jet propulsion to a wider audience, potentially stimulating thought and investment in reaction propulsion research elsewhere, even if indirectly. He helped crack open the door, even if he couldn't walk through it himself. His later work, though less prominent, continued to demonstrate his innovative spirit. His contributions to ramjet and hybrid engine concepts, his understanding of supersonic inlets and nozzle design, all suggest a mind that continued to grapple with the frontiers of propulsion long after the N1 faded from view. Perhaps his greatest failure was not one of engineering, but of circumstance. Born in a nation with limited industrial capacity, working during a period of immense global turmoil, overshadowed by secret, better-funded programs driven by wartime urgency, and pursuing a hybrid technology that was ultimately a transitional dead end, the deck was stacked against him. In the final analysis, Secondo Campini remains the forgotten pioneer. Not because his ideas were necessarily wrong, but because his chosen path, constrained by the limitations of his time and resources, led to an evolutionary cul-de-sac. He built the jet concept into flying hardware before almost anyone else publicly dared, demonstrating the principle of reaction flight years before it became mainstream. His specific innovations in duct burning and variable geometry hinted at crucial future developments. But the torch was ultimately carried forward by those who tackled the harder, more fundamental challenge of the true gas turbine. His story serves as a powerful, poignant reminder that the history of invention is not always written by the victors who cross the finish line first, but also by the brave, often overlooked pioneers who dare to explore the dead ends, who push the boundaries even when the tools are inadequate, who see the future long before it arrives. He was the engineer who dreamed of the jet war era before the war even began, a visionary whose name deserves to be rescued from the footnotes and remembered, not just for his flawed machine, but for the sheer, audacious brilliance of his early vision.